Quick question for you. A big website, hundreds of servers out back, and every so often one of them crashes, reboots, or goes down for maintenance. But when you're browsing, you never feel a thing. So who's behind the scenes, dodging the broken one for you? The answer hides in the few dozen milliseconds between you hitting enter and the backend actually getting your request. That stretch isn't a straight line. It's a series of gates, and everyone is quietly splitting traffic and routing around failures for you. Today, we're pulling that series of gates apart, one gate at a time. Like always, we run it for real. I've spun up 3 backends on my machine with a load balancer in front, and in a bit, right in front of you, I'll kill one of them dead and see whether the client eats an error. All the numbers, live. First, the big picture. From the moment you type a web address into your browser to the backend server actually receiving it, there are 5 gates to pass. First is DNS, translating the name into an IP address. Then CDN, checking whether the content is on an edge close to you. Then it hits the data center, and the load balancer picks a backend. Standing out front is the reverse proxy, the face it shows the world. And only then, the server that does the actual work. Here's the most important line. This isn't one layer of load balancing. It's a whole chain. DNS sits on the outermost layer, the coarsest grain. One name hands you a few his. The deeper you go, the finer the split. By the time you reach the load balancer, it's picking one exact machine. Think of it like catching a flight. DNS decides which city's airport you fly into. CDN checks whether there's a branch nearby, and the load balancer is, once you're in the terminal, you go to whichever check-in counter is open. Layer by layer, guiding you to exactly the point that should serve you. Following the thread from last episode, you might say? Traffic's up? Just add machines, right? Yeah, horizontal scaling. We've drilled that. But once the machines are added, a new problem pops up right away. Traffic. How do you spread it evenly across every one of them? And worse, with that many machines, some are always going to die. A backend crashes, requests keep dumbly slamming into it, and the user eats an error page. So adding machines is only the first half. The second half is this. The entrance needs something to flatten the traffic out for you, and to route around the dead one in real time. That, right there, is the entire reason the traffic entry layer exists. Let's start from the outermost layer, DNS. DNS is basically a phone book, translating a web address into a string of IHs. It comes in several kinds of records. The A record maps a name to an IP, the alias record maps a name to another name, and there's the kind that handles email. But DNS isn't just a lookup. It's the first layer of load, balancing all by itself. One name can hand you back several I's, used in rotation. I actually resolved a few sites. Take a look.
GitHub resolves to one IP, Google to one. But Cloudflare hands back 4 at once, and Wikipedia gives 2. Multiple ITs handed out in rotation. That's round robin at the DNS level. It can also go by latency or by geography, steering you to the nearest one. Note this. The resolver has already picked where you're going before your app runs a single byte.
One layer deeper is the CDN. It takes static content, images, scripts, video, and pushes it to the edge node nearest you, so you don't have to travel all the way back to the origin server. 2 ways to play it. Push. You upload it yourself and manage the updates. Pull. When the first person asks for it, the CDN pulls a copy from the origin and caches it, then goes back to the origin once it expires. High-traffic stuff uses pull. The edge stays warm.
The CDN has a cost. You pay by traffic. And the cache has a time to live, before it expires. Even if you change the origin, users still see the old version. See? Consistency again. The exact same trade-off as that CAP from last episode, just moved out to the edge.
We hit the data center, and the main character steps on stage. The load balancer. In front of it is a pool of identical backends, and its whole job is to pick one. How does it pick? Random, round robin, weighted round robin. Give the stronger machines a bigger share. Least connections. Whoever's got the least on their plate gets the next one. And there's pinning the same client to the same machine every time. Sticky sessions. Talk's cheap. Let's do it for real. 3 backends, 1 load balancer in front, round robin. First, when they're all healthy, let's see how 30 requests split.
Clean as a whistle. 10 each. 3 times 10 is 30. Split perfectly even. 0 errors.
Now I do something brutal. I kill the middle one on the spot. Guess what happens to the client?
This is the good part. The moment it dies, the load balancer's health check picks it up and immediately kicks it out of the rotation. The next 30 requests all go to the 2 survivors, 15 and 15. How many errors does the client eat? 0. Not a single one. Once I restart it, the health check sees it's alive again, pulls it back into the rotation automatically, and it's back to 10, 10, and 10 across 3.
Remember this line. Round robin flattens the load, but what actually makes a dead backend invisible to the user is the health check. That's the soul of a highly available entrance. It's not that nothing fails. It's that when something fails, you never feel it. Now I need to clear up a concept a lot of people mix up. Are a load balancer and a reverse proxy the same thing? No. A load balancer splits traffic across multiple machines that do the same job. You need more than one for it to mean anything. A reverse proxy puts an outward-facing face on your backend. Even if you've only got one machine out back, it's still useful. It hides your backend, terminates encryption for you, compresses, caches, and blocks attacks. In the field, the common tools do both jobs at once, which is why everyone keeps mixing them up. Let me show you a real config, so you can see what this stuff looks like. The top block is the backend pool, round robin by default, but you can switch it to least connections or put a wait on a specific machine. The line below forwards the request into that pool and slips in a header so the backend can still see the real client IP. One more line. If a backend dies, it automatically retries the next one. The whole skeleton of the traffic entry, just these few lines. There's one more distinction between layers you should know. A layer 4 load balancer only looks at IP and port, blindly shoveling bytes, fast, but it can't read the content. Layer 7 understands HTTP, can route by path or by header, can terminate encryption, and can cache. Smarter and a bit pricier. That config we just saw is doing layer 7. But the reverse proxy has a weak spot too. It's the one and only face. So what if it goes down itself? The whole entrance is cut off. So this layer has to make itself highly available too. Active standby, or active-active. Don't let this face become the single point of failure. So in the AI era, how does this traffic entry layer change? 4 questions, same as always, no hype, no trashing. 1. What does it do? It adds a brand new layer of load balancing. Semantic routing, or model routing. Traditional load balancing picks a machine by connection count or by IP. An AI gateway picks a model by the difficulty and the cost of the request. Easy questions go to a small model, or get solved right there at the edge. Only the hard ones get sent up to the big model at the center. The dimension of the split shifts from which machine is free to how much compute does this job actually deserve. 2. What does it replace? It replaces part of the hard-coded rule routing. You used to hardwire forwarding rules by path or by header. Now the gateway can read what the request is trying to do, then decide where to send it. But it hasn't replaced the underlying layer 4 and layer 7. Model routing is a new layer stacked on top of traditional load balancing, not a replacement for it. 3. What does it change? Small models at the edge become a CDN for inference. Think about it. A CDN pushes static content to where the user is. Same idea now. Push lightweight inference out to the edge, out to the device, and only the hard stuff goes back to the center. Latency and cost drop together. That whole keep it close philosophy from CDN moves on to AI, unchanged.
Let me nail down an order of magnitude number. For the same request, mindlessly reaching for the biggest model versus screening with a small model first and only sending up the truly hard ones. The the cost can differ by an order of magnitude. The gate that saves the money sits right at this traffic entry layer.
4. What does it transform? This entry layer grows from mindless forwarding into judgment. It has to understand what a request is worth and where it should go. Put it on the historical map. Load balancing going from layer 4 to layer 7 was learning to read the protocol. Model routing is learning to read the meaning. The same evolutionary line, one more step forward. Who should watch out? The person who mindlessly slams the biggest model at every single request. You're burning cache right at the door. A semantic router would naturally save you a big chunk. 3 pitfalls. 1. TDN cache expiry. Like I said, before the time to live is up, users see the old content. You make an urgent change, and you may still have to manually purge the cache, or it won't take effect for ages. Again, that trade of consistency for speed. 2. Sticky sessions are a double-edged sword. Hashing pins a user to the same machine. The upside is all their session data lives right there. The downside. When that machine dies, every user pinned to it gets hit, and the load gets harder to spread out too. So the more recommended approach now is to move session state out and make the backend stateless, which is exactly what we'll talk about next episode.
3. Don't forget to make the entrance itself redundant. The reverse proxy and load balancer are the path every request must take. If it goes down, the whole site goes dark. It has to be active standby or active itself. Also, DNS changes have propagation delay. Caches are everywhere. You change one record, and it may take a while to take effect worldwide, so don't expect it to be instant.
Let's wrap up. The one line I most want to leave you with today. Traffic entry isn't one layer. It's a chain of finer and finer splitting gates. DNS picks the city, CDN picks what's nearby, the load balancer picks the counter, and the reverse proxy is the face. Every layer is answering the same question. Which point should this request be steered to? The one that ought to serve it. And AI adds a brand new dimension to this chain of gates. Not just by which machine is free, but by how much compute this request deserves. Next episode, we follow the request further in, past the entrance, into the application layer. How one big monolith splits into a swarm of microservices, how they find each other, and what service discovery is really all about. Same as always, we run it for you. Live. I'm Ashley. See you next time.